Evan White, and today I will be presenting to you, Dr. Stewart, a simple analysis of earthquake magnitude. First, let's talk about my data source. My data source is the US government website, the earthquake.usgs.gov, which compiles an extraordinary amount of data about earthquakes around the globe. The data source specifically I've taken from this is an event-driven data bank, wherein even if there were 12 different geological measuring sites triggered by a single earthquake, you only see that one earthquake event on your data source. On the screen you see one of the GUIs they have available to you, but I just took a very simple CSV from this page. Now let's talk about my hypothesis. My hypothesis is fairly simple. It's that earthquake magnitudes are distributed logarithmically along the Richter scale. This means that for every increase in magnitude on the Richter scale, I expect a natural log decrease in its frequency. So I expect it to decrease by a power of e. The way I'm going to test this, interestingly enough, is going to be using simple linear regression. After I apply the natural log to my data set, I can use simple linear regression to see if it fits a line. Simple linear regression, without getting too much into the details, is best explained by this graph. This graph helps you to understand that linear regression focuses on minimizing the residual distances from the regression line, pictured here in green. By minimizing the residual y distances from the regression line, we can assure that we not only have all of our residuals summed to 0, but also have a line that minimizes the total distance from all points. Now, just briefly, we'll touch on the assumptions we're using, since we'll be using them later in the presentation. First, we assume that the two things we're measuring are actually linearly related. Second, we assume that they have multivariate normality between them. Third, we assume that they have none or are very little multicollinearity. They have none of that. Also, we assume there's no autocorrelation. One does not affect the next time-wise, which is pretty safe with earthquakes. And lastly, we also assume homoscedasticity, which is simply a unbias in the, we need to assume an unbias in the distribution of the residuals versus the fitted points. So here's our raw data. We have 17,050 data points with quite a lot of information about them, but we focus really just on the magnitude for our purposes. So the first thing I did is I went ahead and did an initial linear regression here. You can see we have a trend scatter for the magnitude that doesn't seem to indicate a strong presence of a line at all. And when we put in the line, we see that our line is outside of our data point as often as anywhere near it. So this is just the initial one without doing any logarithmic manipulation. And so then we look at the residuals versus the fitted. We see the residuals are really not homoscedastic. There we go. And we also have our QQ plot, and it is absolutely not normal. This will persist throughout, but we'll be able to fix the residuals in fitted position. So if we look at these assumptions, it's definitely not linear. Multivariate normality is not a go. Collinearity, we're pretty safe on. Autocorrelation, pretty safe, but homoscedasticity, absolutely not. So then we did a second one, where we actually just put the natural log of the data and then tried to fit that. As you can see, it's a lot closer, especially up until it gets this knee area. However, its R-squared value still isn't fantastic. It's only about 0.03 or 0.03 larger than our previous, mostly because of this tail here. So if you look at the residuals versus fitted, they look pretty good up until that tail, and the normal plot looks pretty standard for what we'd expect. Although, to be clear, it's absolutely not normal, and the data versus normal distribution, the Shapiro-Wilk normality test informs us that this is not a normal data set, just like the predecessor. So I took it one step further, because I felt like had this bend in the data not existed, we would have had a linear relationship. So I actually removed elements with less than 1 Richter magnitude, which is kind of where that knee in the graph existed before. And now when we look at our trend scatter, we actually see a very, very noticeable line straight through our trend scatter. We're not really outside the realms of the reasonable confidence intervals of the trend scatter for very long at any point. Also, when we look at our actual line we draw, our regressed line, we see that its R-squared value is 0.94, which is actually pretty high, and its total digression from the mean is quite small. So, running through the analysis on this tertiary regression, we see that our residuals versus fitted are actually pretty good, and the QQ plot remains extremely bad. Now let's analyze this one in a bit more depth. There are actually quite a few assumptions going on to create our linear regression model. So the first one is we have to be actually linear. And in this case, this last case, it seems reasonable that it is linear throughout. It also needs to be the case that we are multivariate normal. However, we are certainly not. Going back a slide, these back to the p-value of 0 and the data versus normal distribution make it pretty clear we're not normal, multivariate. Not multivariate normal. Our sample size is large enough though. Standard practice says that sample size should be at least 20 for every independent variable you have. We have one independent variable and we have 17,000 observations. We're fine. We've also removed outliers by taking only those within 2.5 standard deviations of the mean, and outliers can really bother linear regressions. As far as multicollinearity goes, we don't actually have the tools, or I don't have the tools to measure it. I looked up the VIF function and failed to effectively utilize it. However, we can say with pretty reasonable confidence that we don't have any autocorrelation, given that earthquakes do not relate in any sense one to the other. There's no effect of one earthquake on another earthquake, so to speak. And then homoscedasticity, as we've measured in the previous slide, is actually quite reasonable. So, what are the conclusions we can make? The first conclusion is it is absolutely not, in its base form, a line. We know that there is significant evidence against the fact that this data is a line right out of the box. There is some not negligible data to argue that it does in fact follow a logarithmic path a linear path after you take the logarithm of it. However, because we've never actually established that multivariate normality, it's not 100% clear to us that we can say it is a logarithmic scale with this logarithmic value and then it follows a linear trend safely. So we can say that there's absolutely no chance it's linear data to begin with, but we can say that it's more likely it's logarithmic than that. If I were to move forward with this project, I'd have a couple things I'd like to do with it. First of all, expanding the timeline. If I were able to expand the timeline by more than 30 days from here, not only would I have a lot more data to work with, but I think I would be able to better ascertain whether some of these were mistakes I made or perhaps just flukes in the data. Second, I'd like to utilize more histograms. Currently, there aren't that many histograms in the project. Mostly, I did a incidence map, just because there was so much data that you didn't need histograms to show the general picture. And third, I think it'd be really cool to segment this data. We have so much information going on. If we go back to the beginning here, we have an amount of data that is truly ridiculous. We have 23 different variables filled out for almost every single one of these. So it'd be really cool, in my opinion, to take our data, segment it perhaps by location, and talk about all the things that happen in South Orange County Beach, California, or talk about all the things that happened in the year 1995, that sort of thing, or all the things that occur within 1 kilometer of the epicenter. So with that, I thank you for your time and hope you have a wonderful Christmas break.